Let me just share my slides. Okay, yeah. Thanks for the invitation. We're very, very happy to be here and to talk about some work we did last year on fault-tolerant Steane quantum error correction. So I will start with a brief introduction to Steane error correction and show some of the results. And then Vanya will take over and discuss the experiment in more detail. Okay. So yeah, the general idea in quantum error correction is to encode information not on a single physical qubit, but on multiple qubits, so that if some error occurs and, for example, a qubit is flipped, we can still recover the initially encoded information. And one example are these topological codes where information is encoded in these global degrees of freedom. For example, in this case, loops around a torus. And if now some error happens on a qubit, for example, sitting somewhere here, the idea is to first localize these errors by measuring local operators. And then in a second step, try to remove this error by applying a suitable correction operation. And this is often done with stabilizer codes. So stabilizer code is a code where a quantum state is not described by all the entries, by all the explicit entries in a state vector, but by a set of commuting operators or stabilizers. And the valid code space is then spanned by all the simultaneous +1 eigenstates of all of these stabilizers. So if we start with the initial code state and some error happens, this valid code state gets mapped into an orthogonal subspace. And if we then measure all the stabilizers, we'll find that we get a -1 outcome for some subset of these stabilizers. And based on this pattern of measurement outcomes, we can then try to guess the initial error and map the state back into the code space. But if one looks at the implementation of these error correction protocols, this means that the stabilizer extraction process itself has to be reliable, meaning that errors should not spread too far within this procedure. And for this, we can use these fault-tolerant circuit designs, which ensure that errors do not propagate uncontrollably. And there are essentially two main approaches which are often used. One of these is flag-based quantum error correction, and the other is Steane quantum error correction. So here I only cite very few examples where these protocols were implemented, but there are, of course, many more. So I will not talk about flag-based quantum error correction in detail, but just to sketch the idea. So in this case, one uses physical auxiliary qubits and essentially maps stabilizers from a data qubit register onto these auxiliary qubits. And then one measures these auxiliary qubits and from that can infer the stabilizer values. The main idea in Steane quantum error correction is to use logical auxiliary qubits and transversal gates. So to shift this around. Transversal gate is a gate that can be implemented in a bitwise fashion. So for example, if we have two logical qubits, qubit 1 and qubit 2, the transversal CNOT gate could just be implemented in the CSS case by applying physical CNOT gates on pairs of qubits, as shown here. And that means if some error is sitting, for example, on this data qubit here, this propagates through the CNOT, but it does not propagate within one encoded block, meaning that this initially correctable error stays correctable. So in the following, I will now talk in more detail about Steane quantum error correction and the general procedure, and then show some of the results that we found in our work last year, and then hand over to Vanya, who will talk about the experimental setup and some challenges in detail. And of course, if you have questions, please just interrupt at any moment. Okay, so this is the general construction for Steane quantum error correction. So we start with a logical encoded state psi here. And in the first step, we initialize a logical auxiliary qubit in the plus state. So at this point, we are in a logical product state of psi plus. Then in the second step, we apply this transversal CNOT gate and couple the data qubit register with the auxiliary qubit. In the fault-free case, this just acts trivially on our state. So we just stay in this product state of psi plus. But if there's some error already present, so as I showed before, this transversal CNOT just contains pairs of physical CNOT gates. So if some error is sitting on a data qubit here, this propagates, as I showed before. But what it does is it effectively copies this error which was sitting on the data qubit onto this auxiliary register. So if we look at the state, so now we have this error sitting on a data qubit, so an X error on qubit I. This is just copied with a CNOT gate onto our auxiliary qubit. So we end up in this state here. So what we do in the last step is we measure this auxiliary qubit in the Z basis. And from that, we can then directly extract all the Z stabilizers. And based on that, make a guess about a suitable X correction. I will also show an explicit example in a few slides to make this more clear. Yeah, but this is only the first half of the protocol because, of course, we also want to correct Z errors. So what we do is, after we did this first part, we repeat the same thing, but now initialize the auxiliary qubit in the logical 0 state and basically flip the CNOT so that we effectively copy Z errors now from the data to the auxiliary register. And then in the last step, one has to apply the correction to the data qubit register based on the stabilizers that were extracted in these measurements. Yeah, so what we did is we now looked at different codes and implemented Steane quantum error correction. And one example is the repetition code. For example, the 3-qubit bit flip code, where we have 3 physical qubits, and the stabilizers are 2 Z stabilizers, Z0, Z1, and Z1, Z2. It means that the logical 0 state is just 0, 0, 0, and the logical 1 state is just 1, 1, 1. And now we can just apply the scheme that I showed before. So we start in the logical state psi, which in this case, we just looked at the logical 0 state, because in the bit flip code, you can only correct X errors anyways. So we initialize the logical auxiliary in this equal superposition of 0 and 1. And if now an error is sitting on, for example, qubit 0, this is copied onto this auxiliary register. So after applying the CNOT gate, we are in this state 0, 1, 1 plus 1, 0, 0 plus 0, 1, 1. So if we then measure in the Z basis in the end, we can extract the 2 stabilizer values. So we get an odd parity looking at the first 2 qubits here. So we get a -1 and even parity for the last 2 qubits. So we get the syndrome -1, 1, which indicates lets us assume that a single error has occurred on qubit 0. So we correct this. So in the bit flip code, we can only correct X errors, but this works completely analogous for the phase flip code for Z errors in that case. So what we did is we looked at the distance 3 and the distance 5 version of the bit and the phase flip code and determined the logical fidelities after multiple rounds of Steane type quantum error correction. And this is what you can see here on the right. So panel A corresponds to the bit flip code and the lower one to the phase flip code for up to 5 rounds of error correction. So here, 0 rounds of error correction just corresponds to the pure encoding. So we just initialize a logical state and that's it. So here we can now see, different things. For example, I forgot, the darker bars here correspond to the experimental data, and the lighter bars correspond to the simulation that we performed. Okay, so first of all, we can see that the phase flip code achieves lower fidelities than the bit flip code, and this is just due to dephasing on idling qubits. Which does not affect the bit flip code because, if you look at the 0, 0, 0 state, a Z error doesn't do anything to it effectively. Which is why we only see this drop in fidelity due to dephasing when we look at the phase flip code. And second, we also see that fidelities increase when we go from distance 3 to distance 5, which means that in this regime for this code, we are effectively operating below the pseudo threshold of this code. So in the next step, we went one step further and looked at a fully error correcting code, namely the 7-qubit color code. So in this code, there are 7 physical qubits that encode a single logical qubit, and we have distance 3, which means that we can correct any single X, Y, or Z error. And the stabilizers are now defined completely symmetrically on the 3 plaquettes. So we have a red pair of, so a red X and Z stabilizer, a green one, and a blue one. And for this error correcting code, we now looked at 2 different versions for quantum error correction. So first, we looked again at Steane quantum error correction, which is depicted here in the upper part of this picture. So here we have logical auxiliary qubits, and as I showed before, we copy errors to this auxiliary logical with transversal gates. And second, we also compared this to a state-of-the-art flag-based scheme, which is taken from this reference here. And in this case, we now use a physical auxiliary register and basically map the stabilizers from the data qubits to this auxiliary register, and in between flag potentially dangerous errors. So we now again implemented both of these schemes and performed experiment and simulation, and then extracted the logical fidelities for multiple rounds of error correction given different logical input states, as shown here. So the upper plot shows the fidelities for the logical 0 state, and the lower one for the logical plus state, up to 3 rounds of error correction for Steane quantum error correction and then flag-based quantum error correction. And now we see that, Steane quantum error correction achieves higher fidelities than the state-of-the-art flag-based approach. And this difference is more pronounced for the logical 0 state than for the logical plus state, which is, again, due to dephasing, which basically annihilates some of this advantage that we get. And the reason why Steane error correction is advantageous is because in this scheme, we basically minimize the interaction of the data qubit register with the auxiliaries, because we really only have these 14 CNOTs that act on the data qubits, whereas by this flag-based, you at least have 28 qubits, CNOTs acting on your data register. And what we did is now to basically filter out this effect and pin this down a bit more, we ran some additional simulations where we only look at noisy 2-qubit gates, meaning that all other error rates are just set to 0, and we have no idling, no dephasing on idling qubits. And this is what you can see here. So now this is only simulation data now. And on the one hand, we see that this difference between logical 0 and plus vanishes because we don't have dephasing anymore. But also the difference between Steane and flag quantum error correction is now more pronounced, which means that we have this advantage of Steane quantum error correction or with logical qubits and transversal gates over this flag-based approach. And in the regime of dominating 2-qubit gate error rates, we expect that Steane quantum error correction is advantageous. However, to get into this regime, there are, of course, still many experimental challenges. And this is where I hand over to Vanya to talk about the experiment.
All right, while I'm switching on, you can ask some questions.
Yeah, I have a... Sorry,
in the resources, so it seems that indeed you might get better performance with the Steane error correction, but you need like at least 6 more qubits or maybe 4 depending on how you use the flags. And then also you need to prepare a second logical qubit, right? Whereas in the flag you don't need to prepare a second logical qubit. And so how do you think like time-wise and resource-wise this compares?
I think there's not a that big of a difference. So in terms of the gate count, even if you include the initialization of the logical auxiliaries, it's the same. I think there's one gate difference compared to this flag-based approach. And for the state-of-the-art flag error correction scheme that, for example, Quantinuum used, you also have 6 + 1 auxiliary qubits. So you also have the same number of auxiliaries in this setting. Of course, you can also do readout stabilizers sequentially, but then you have much more idling periods and so on. So I would say overall, it's not entirely clear.
Maybe I can add that there's also a trade-off between, so to do the stabilizer readout, you need a mid-circuit measurement procedure, which I will be talking about. And of course, it has finite fidelity in experimental case. And it's a trade-off between how many spare qubits you have and how good your fidelity of mid-circuit measurement is. So if it's perfect, you might, do the sequential stabilizer readout and just only use 2 auxiliary qubits, for example. While if you have a lot of qubits, but your mid-circuit measurement is poor, you would prefer to, map it all at once, for example.
Okay, thanks. I
So
think Jonathan has a
it
question.
depends on the, details of the setup and what fidelities you have for different operations. Yeah, sorry.
Yeah, I had a quick question, Frederica. In your simulations with just the 2-qubit gate infidelities, in the flag-based scheme, it seemed like the dephasing was affecting the bottom row, which I guess was the X correction rather than the Z correction. Like different between the two, and I just wondered if you have an intuition for why that was.
I can share the slide again. Sorry. Here?
Yeah. Are they different or are they the same and I'm misreading it? So
I think they are the same, but I will check again.
okay.
They should be the same. Yeah.
I see. Okay. Thanks.
All right, then I guess let's come to the experimental part, which I was told that you would be interested in details, how this procedure and error correction is done experimentally. So I will try to focus on that stuff. Can you see the slide and all of the things? Okay, cool. So so I was told by my colleague Christian Marciniak that he gave a lot of details about our setup in Jonathan Holmes' retreat. So I think I will not focus too much on our general setup description, although I will list some of the features. Well, mostly I will be talking about this mid-circuit detection procedure, which was essential for the paper Frederica presented. And how we did it experimentally, because that's basically a roadblock and the missing feature we didn't have before that paper. So in general, the idea of our setup was to make a step from standard lab environment to something more industry compatible. So our setup is assembled in 2 19-inch racks. The project is called Action after the EU project. So mainly we wanted to focus on remote access and low maintenance for the setup, such that you don't really need, let's say, PhD students who oversee the setup all the time, but instead you can mostly calibrate it remotely, and you don't need to do a lot of alignment of the lasers manually. And that was one of the goals. So you can notice that we don't have any optical table in the setup. So our trap here, it's sitting in this right rack on active vibration isolation stages, which are comparable in performance to the optical table, as it turns out. Most of the optics and elements are quite compact and either assembled on this breadboards, small breadboards, or in this modular fashion with this cassette units you can see here. And as I mentioned before, we tried to make all the devices, RF control, laser control, remotely accessible, such that you can do it without physical presence in the lab. Yeah, and basically, whole setup is sitting in these 2 racks, and doesn't really need any cryo environment or special cooling conditions, just reasonably well AC conditioned room, and you just plug it to the socket and connect to the internet, and it's good to go. One of the features I think which will be important for future considerations for mid-circuit detection is how we address ions, and for that we use optical addressing for single ion addressing using two crossed acoustic optical deflectors. I hope you know how this device works. If you don't, feel free to ask. But the idea is that we have them crossed at 90 degrees like this, and if you supply the same frequency to both of them, they move your spot somewhere here. While if you change both frequencies by the same value, they steer it along the line, and you can address a second ion in a linear trap. So one of the deflectors is working in the first diffraction mode to the first diffraction mode, and the second one to the minus first mode. And in that case, we don't really have any frequency shift, and we can address two ions simultaneously if we supply a couple of frequencies to each deflector. We can also move the beam vertically if we kind of add the difference to these frequencies, but that will change the absolute frequency, and you need to account for it. But overall, we can do simultaneous addressing of two ions, which is good for 2 qubit gates, and we can individually adjust phase and power for every ion. So of course, one of the problems of optical addressing would be optical crosstalk, and when you address one of the ions, neighbors, I guess, unavoidably will see some excitation. And you can see that this addressed ion sees relatively fast Rabi flopping, and the neighboring ion sees something like 50 times slower. But there is this effect. And in the following, I will define the crosstalk value as the ratio of Rabi frequencies of unwanted excitation to what we actually want. So we did a characterization for 50 ion chain in our setup. So this is the matrix of these crosstalks. And I zoomed in this part. You can see that the largest number in the whole matrix is about 3.5%. So on average, it's lower. So I guess we can say that we can work with the long ion chains in terms of addressing performance. The previous setup in Innsbruck had this value several times worse. Yeah, so optical addressing is not the problem. Although we mostly work with 16 ion chain, not 50 ion chain, because our main limitations are 2 qubit gate fidelities and how to do gates in a large or like medium chain rather than optical addressing setup. So yeah, I guess most of you know calcium scheme. So we also work with calcium 40. Our qubit is encoded in this optical transition, S1/2, D5/2. And the single ion addressing setup I mentioned, it's working on 729 nanometers. But everything else is relatively standard. So detection is done on SP transition with repumper 866, and qubit reset is done with 854. So we also have an RF coil for the ground state qubit, which we will use for dynamical decoupling. And I will mention this later. Also, I wanted to describe our native gate set because it will be important for, well, error correction, basically. So we can do arbitrary rotations, single qubit rotations. So XY rotations we do by doing a resonant transition, where we control the angle of rotation by the length of the pulse and phase by the phase of the pulse. Z rotations we do virtually, which I think is quite popular now. You just change all the subsequent phases of future pulses. Yeah, and basically it's a perfect operation with fidelity of 1. For 2 qubit gates, we do Molmar-Sornes interaction, which I think you're also familiar with, where we have a bichromatic beam, which is slightly detuned from one of the motional modes of the ion chain. So in our case, it's radial motional modes, because our addressing comes perpendicular to the ion chain. Yeah, and then if you choose all your parameters correctly and the tuning and the gate time and the power, you will end up in a mixture of SS and DD without any excitation left in the motional mode. And that's I guess, the ultimate goal, because this XX gate is equivalent to CNOT up to local rotations. So in terms of fidelities, we have around 99.5 for single qubit gates based on randomized benchmarking. For 2-qubit gates, it slightly varies from pair to pair, but on average, it's around 98.6. And for other operations like initialization and readout, it's above 99.7, and that's currently not a limitation. I guess last parts I would also mention about the setup is that all these fidelities are maintained by a sequence of automated calibrations, as I promised in the beginning as one of the goals of the project. And yeah, so by running this kind of sequence set of calibrations, we ensure that fidelities are kept at the same level, and those procedures only take 20% of setup's time, so that's like illustrates the duty cycle, and 80% of the time on average you can do, you know, error correction and run quantum computing algorithms whatever you want, which we can do with Qiskit interface, which was developed in collaboration with AQT, our startup in Innsbruck. Basically, you can just give us a Qiskit circuit and we can submit it to our device in a cloud access fashion. We don't really use it as a cloud access for open access, but we mostly use it for collaborations with theorists. So yeah, that would be roughly it about the experimental setup in general. We of course can discuss more details if you want to. And now I would like to get to the point where we were before this paper about Steane error correction, because we didn't have any mid-circuit operations, so we couldn't do mid-circuit measurement, because Friederike shows you a lot of circuits with something like this, and it has this place, meaning that you want to read out some auxiliary qubits, reinitialize them, and continue. So we couldn't do that before, and that was obviously a big limitation, which we had to overcome somehow. So let me formulate a task for this procedure. So we have a register of qubits, which we virtually split into data qubits and auxiliary qubits. So what we want is we want to read out auxiliary qubits. We want to keep state of the data qubits undisturbed. We want to reinitialize auxiliary qubits. And then we want to recool the chain, because when we detect, the chain heats up, and fidelities of the future MS gates can be spoiled. So we need to make sure that fidelities of the gates are as good as they were before. The problem is we have a limited amount of tools. Basically, the only addressed interaction we can do is 729 interaction. So we cannot just, detect with 397 and 866 in an addressed way. We don't have a capability. We have limited optical access, and our setup is very compact. So we have to somehow deal with this set of tools, which create some issues. So let's have a look again at our level scheme. As you can see, qubits are encoded in this optical qubit here. And the problem is, if we do detection with our global beam, or if we do qubit reset with our global beam, we will spoil states of data qubits. So we will also detect them or reset them. That's why we need to do some kind of hiding. For example, when we do detection, we can put our data qubits in this D level, and it will be untouched by 397 light, as well as 866 light. Same for qubit reset, sideband cooling, pumping, and all of that stuff. We can hide it in the ground state qubit, and then this global 854 beam will not reset our data qubits, while the address beam, it is addressed. So we can select which qubits we excite with it. All right, so let's try to do this. I'll quickly go through the full procedure of how we do this mid-circuit measurement. So first we start in standard encoding for both qubits. Then we hide our data qubits for detection. So we use this RF coil to move this one up here, and then addressed one by one, we move all data qubits in here. So we end up with data qubits being here. Now we can detect auxiliary qubits. We use 397 light. We get some counts on the camera. We know the result of the measurement. And now we want to reinitialize auxiliary qubits and cool the chain. For that reason, we will need to hide data qubits to the ground state, such that we can do pumping, sideband cooling, and qubit reset. So we will do it again with address beam one by one. They will end up here. So now we can do pumping, we do it with 729 and 866 by 854, sorry, by rotating qubits. Then we can do sideband cooling. Both of those procedures do not disturb data qubits. And we will end up with something like this, with auxiliary qubits initialized and the chain cooled. And now we need to unhide our data qubits to move them back to how it was, and we will end up with the desired configuration. So overall, it will look something like this. So first we do hiding of data qubits, which would be this global coil pulse. A lot of single qubit pulses because we move them one by one. We do this address 729 on each qubit. Then we do detection, global operation, Doppler cooling, global operation, unhiding, and then hiding again for the cooling and reset. So again, a lot of address pulses and coil pulse. A lot of cooling pulses, because unfortunately, due to limited optical access, we don't have any efficient broadband cooling. So we only use sideband cooling, and that is usually narrowband, and we need to do it for every single mode we have. And for 69 chain, it would be 32 modes. So we need to do a lot of those pulses, pump and initialize our auxiliary qubits, and then we unhide data qubits. So overall, procedure would take about 20 milliseconds, which is quite long for compared, for example, to two-qubit gate operation, which is 300 microseconds. And we have a lot of address pulses on data qubits, which might be an issue. So let's keep this in mind. So far,
sorry, can I ask something?
Yeah, sure.
I'm just confused about unhiding and hiding part, because
yeah. Do you want to go back here?
Yes. So you hide it into a different.
Yeah. So when we do detection, we want no data qubits to be in S level or P level, right? So we will move them to D. So 397 will not disturb them. There is also 866, which is not shown, but it only touches D3 half. It does not do anything to 5 half. Does it make sense?
No, I meant like you have an hiding and unhiding next to each other. Why not unhide at all?
Well, yeah, that's just basically an illustration of how exactly we do it. So if we look here, for example, here, it's just we found it working better to do it with the coil pulse, and this step looks slightly different in reality. So we do basically this and then reverse of this in some sense. But yeah, this is technical. You can okay. Also like merge it into one, and it will be fine. Like you can call it re-hiding, for example.
Okay, I understand. Thank you.
Yeah, but it's not a big deal. It's just it worked technically slightly better. I think it doesn't matter that much. We could have also done it by how I showed it here.
Thank you.
Yeah.
Can I also ask a quick question?
Yeah, sure.
So when you're hiding and stuff, but then you have these global beams. So I guess there's an AC Stark shift, and I guess you're picking up a phase somehow or so.
We do characterize it, but I don't think it plays a major role, to be honest. So what Stark shift from which beams do you have in mind?
I don't know. So I have to look at this more closely. But when you're hiding for detection, so to say, the detection beam is 396, right?
396, yes. Yeah. I call it 397. Yeah, this one.
Well,
but it's resonant. You mean that 397 interacts with D5 half S1 half?
I think, yeah.
I think it's pretty small, and yeah, and also this one is quadruple, and this one is very far. I don't think there is any.
So you don't see a problem from that? It's the conclusion.
I think no. I don't think we have any issue with this, but we do characterize errors of the procedure and take this into account. So if there were a Stark shift from this, we would take it into account. Yeah, but I think it's also negligible, to be honest.
Okay, thanks.
I guess you would only care about.
Yeah, you're muted.
Where you hide, right? So then, sorry, I guess you only care about differential Stark shifts in the two green ones, and for 397, those should be kind of similar, right?
Yeah. I think main problem with Stark shift would come from crosstalk from these address beams, which I will comment on, but I think mostly it's those, you know. Basically, when you do cooling, yeah, I will talk about this in a second.
I also have a quick question about the hiding. Why do you have to do an RF with these 729 address? Can't you just do it directly?
Yes, yeah, that's
a beam geometry thing.
Yes, that's a good point. So kind of beam geometry thing. So we made our polarization such that this address beam doesn't have any delta m equal 1 component, plus minus 1.
Yeah, right.
Because, well, this is a tricky question, but we saw that gate performance becomes better when there is no such component, probably because two Stark shifts coming from that. Yeah, we don't really have, I think, a kind of pinned down model why it is like this, but we just saw better performance without those components, so we had to, you know, change polarization for that. And yeah, well, we thought it's okay since we have a coil, because it can, you know, do this additional +1, let's say.
Yeah, okay, thanks.
All right, then I will continue. So yeah, so far I see 3 issues with this procedure. So first, this crosstalk I mentioned. So when you do sideband cooling here on this ion auxiliary qubit, you might somehow spoil the state of the data qubit here, which we saw an effect from, and we decided not to cool on 1 or last 2 auxiliary qubits, and we didn't see that it hurts the cooling performance that much, but yeah, that was one of the issues we had. So second issue is that we don't have a great coherence time, as Federici mentioned, for, you know, some reasons we can discuss later if you want, but it is the case, and when we move both data qubits in here, they decohere much faster than in -1/2, because this is more sensitive to magnetic field noise and so on. So we decided to do dynamical decoupling while qubits are hidden. And third issue is that I mentioned that we need a lot of hiding pulses, address hiding pulses for data qubits, and of course they have finite fidelity, and you know it adds up. So we also thought that we should do something about this, and we will talk slightly about composite pulses, how we can try to mitigate it. So let's start with this dynamical decoupling thing. I guess you all have heard about what it is, but basically it's doing this echo sequence. You can, instead of waiting for a long time while your qubit is dephasing when it's in equal population state, for example, you can add this pi pulses, do this echoing, and position it such that it has equal intervals in between. And then you can basically preserve your coherence perfectly. Optimal time between these pulses depends on your noise structure, but for us it's relatively slow noise, so I guess anything, well, something around 1 millisecond is totally fine for us if we do these pulses like every 1 millisecond, maybe even less frequently. So what we did, we took this like smaller F coil, which we inserted really close to our chamber, basically touching our viewport such that it can reach the whole chain, ion chain. And here you can see the Ramsey contrast versus waiting time on the ground state qubit, which is really poor, on optical qubit, which is better, and on ground state qubit with spin echo with the dynamical decoupling sequence, which is basically perfect. So that's what we should go for. We need to apply the same thing in our mid-circuit measurement. Well, that's what we do. We just insert this echo sequence in between those pulses in mid-circuit measurement procedure, and yeah, let's just see how it works. So ideally, if we like do all the timings correctly, it should preserve the coherence much better. So here you can see we are testing it with 69 chain, and we detect half of the chain as for the Steane paper, basically in a similar way. So first we start with the blue curve. This is no recooling at all, so that's what we expect, how it should look like immediately after initialization. So then now if we do recooling, but we don't do any echoes, the coherence is terrible. as we expect, because the ground state coherence time is 5 milliseconds and procedure takes 20 milliseconds. So we expect it to be nothing. But when we introduce this echo sequence, you can see it recovers almost back to the same value. So it definitely helped this echo pulses. Second question is if cooling works well or not. For that, we wanted to test gate performance in the chain. So we prepared a GHZ on either part of the chain before the recooling, which shows around 86% fidelity. And then we tried to do it on auxiliary qubits and data qubits. And you can see that on auxiliary qubits, after the recooling procedure, GHZ is fine. It's roughly the same as before. But on data qubits, it is not as good, meaning that we'll probably somehow corrupt the state of data qubits while we do this procedure. So we did a tomography for data qubits, like what this procedure does to data qubits, while ideally it should be identity. But so this is average result over multiple qubits, and you can see that it's like 93% of identity, and then there are some errors. So that might be due to just a lot of hiding pulses, and then due to decoherence during our Doppler cooling and detection, because there we don't really have a good way to do echoing because they are sitting in the D level. Well, that's an issue, but nevertheless, we can try to address at least the first one by doing composite pulses. And by that, I mean, instead of doing normal pi pulse, we can do a sequence of pulses, which essentially should do the same, also a pi pulse, because those are 2 pi pulses, they do nothing. But the way it works, it becomes more robust to first in density fluctuations. So that's the desired amplitude we want to have. And you can see it becomes flatter in this region. And second, it's more resilient against crosstalk because at low amplitudes, it has lower excitation, meaning that neighboring qubits will also suffer less. Sounds great, but unfortunately, our current hardware cannot do a lot of pulses. It just starts crashing, and we cannot do the full procedure and the full Steane error correction business on the current hardware, but we are already switching to another hardware, and hopefully it will work out. So yeah, summarizing the results of this procedure. So first, overall it works, and we use it in the paper, as you can guess. Echoes help a lot to preserve the coherence of the qubits to mitigate our poor coherence in the system. We also are happy with initialization of auxiliary qubits, and recooling is also fine. While for the issues, the procedure is quite long, which I guess can be solved by introducing a better, more broadband cooling mechanism, which we cannot have due to limited optical access, but in principle, it's not a limitation. We do have this partial corruption of data qubits, mostly due to a lot of hardware, a lot of address pulses, which can be mitigated by composite pulses. And we definitely should improve our coherence time, which is just low by mistake. And now we are doing hardware upgrades to make it better. So those are the first 2 things we're working on now. And let's see how it improves. I really hope that this procedure will be better. So now getting back to your question about comparison of Steane and flag qubits. So you can see in this particular setup, mid-circuit detection is not very good in terms of fidelity. So it would be better probably to have more ions and do mid-circuit detection less frequently. While if you get it perfect, you can get away with fewer qubits, I guess. For example, I think for quantinum setups, I believe that mid-circuit detection is easier and works better. And that would be not an issue. They can probably do small, readouts 1 by 1, something like this. Yeah, so we successfully applied this procedure in these 2 papers. So one is this Steane error correction paper. Second one is code switching. So it allows us to do a lot of stuff we couldn't do before. And I guess next step, which will unlock more opportunities for us, would be mid-circuit decision making, which is also work in progress currently. And hopefully we can make it work. So that's the team in Innsbruck, those who work in the action project, and I'm happy to answer your questions. Thank you for the attention, and feel free to contact me later if you still want to discuss something. That's it.
Are there any questions? Because we had already a few questions, but if anyone else has questions.
Yeah, like, do I call people, or because I see raised hand? Are you moderating this, or shall I do?
No, I think people can unmute themselves as before. But I think there's not more. I think there was already a few in the talk.
Maybe I could also just briefly comment again on Jonathan's question from before on is there a difference for the different logical states? So there is a very small difference, which depends on the ordering on with which you read out the stabilizers. So in the Steane error correction, do you first read out check X errors and then Z errors, or the other way around? But this, in our case, this difference is very, very small compared to the so the relative difference is small because you have large 2-qubit gate error rates.
Thanks. Yeah.
Yeah. A bit unrelated to the whole Steane error correction, but more on the recent works from Marcus Miller's group on the measurement-free error correction. Do you think that's something that you would like to do in your setups, or?
Well, I haven't read this paper yet, but yeah, sure. I mean, I love working with Marcus Miller and his colleagues, so whatever they have in mind, I'm happy to try to implement.
Yeah, I would also be happy.
But like, how much more difficult would it be? I don't know if you have an idea, or I don't know. Maybe Federica, I don't know.
Yeah. So in this work, we would need more qubits, which at least more than 16 for sure. So to really do something new with that. So it depends. So if you have more qubits available, then maybe.
Yeah, well, we're working on this right now. So
cool. Yeah, thanks.
Okay, then thanks a lot to everyone, and hope to see you in 1 month for the next talk.